Okay, and so here's a sample problem for APC level because we're going to deal with calculating work with a non-constant force. And so this one's going to be pretty nondescript. What we're going to do is I'm going to give you a function for our force. Force is a function of position equals 10 newtons plus 3 newtons per meter squared times x squared. So if I plug in some value for x, I can find what the force is. For instance, if I find f of 0, I end up with 10 newtons plus 3 newtons per meter squared times, I put a 0 in there, that's a whole lot of zeros, so I end up with 0 newtons. My initial force is 10 newtons. Or I could evaluate it at 1 meter. I plug that in and you'll find that it's 10 newtons plus 3 newtons equals 13 newtons, and so forth. You could put in 2 or 6 or 90, okay? So for this, we have a nondescript, just a function for our force. What I want is I want to find work as a function of position. Okay, so I'm going to ask for basically so I'm going to find work as a function of x. So what I'm going to do is, we know that work in general is the integral of f dot dx. I will also tell you that in this case, our force is in the positive x direction. So it's going the same way as a given displacement, okay? And we can also see that from our equation. Oh, no, okay. But it's going in the positive x direction. We'll go ahead with that. So that takes care of our dot product. They're pointed the same way, so we'll end up with the magnitudes of the two of these. Work equals f dx just times 1 cosine of 0 degrees. And so we can totally ignore that. All right, so I've got a situation where my work equals the integral of f, so I'm going to take my force as a function of x, and I'm going to replace it with what it actually is, 10 newtons plus 3 newton per meter squared times x squared dx. All right, technically I'm going to evaluate this from x equals 0 to some final position, x final, which we're just going to leave blank as a variable for x. But it's bad form to evaluate an integral with just a nondescript x being the variable that we're integrating. It's calculus rules, but we'll stick with it. I've been chased by enough mathematicians armed with textbooks that I think we'll go ahead and do it this way. So I can spread this out. I'm going to distribute my little dx guy, and so I can treat this as the integral from 0 to x final of 10 newtons dx plus the integral from 0 to x final of 3 newtons per meter squared x squared dx. Well, 10 newtons and 3 newtons per meter squared, these are both constants, so I can bring those out. This is my work equals 10 newtons times 0 to x final dx plus 3 newton per meter squared 0 to x final of x squared dx. Because I can pull my constants out of the integrals here. All right, well, I evaluate these integrals. This guy just becomes 10 newtons times x evaluated from 0 to x final plus 3 newton per meter squared times, this guy is going to be 1/3 x cubed evaluated from 0 to x final. Okay. Well, that would be 10 newtons times x minus 0 plus 3 Newton meters squared times 1/3 x final cubed minus 1/3 x initial, 0 cubed, which is a whole lot of 0. Okay, almost there. We end up with 10 newtons times x plus 3 Newton per meter squared times 1/3 x final cubed. End up with 10 newtons times x plus, these 3's cancel out, and I'm left with 1 Newton per meter squared times x final cubed. So, oops, not x final. Look at me, bad form all over the place. Yeah. Okay. So, this is what my work is. My work equals 10 newtons times whatever arbitrary final position of x. So, this is basically just my variable x, because I could say anything from, if we start at 0, we go all the way to 7 meters. Or I could arbitrarily say 8 meters, or 3,647 meters. I can plug in just about anything, so this guy is just my variable x plus 1 times Newton, 1 Newton per meter squared times x final cubed. So, since these are both just a nondescript placeholder, they're a variable, that's my work as a function of x. Now you'll notice that I left these units in here. I've carried this 1 along because there's an important reason. This is 10 newtons times some value x in meters, that'll be newtons times meters, so this will have units of joules, plus this is Newton per meter squared, this will be times meter cubed. Well, the meter cubed is going to cancel out the meter squared on bottom and have 1 meter left over, that's newtons times meter, joules. So this coefficient is important. Don't lose those units. That's why I've kept that 1 in there. Now I've used x sub f, so my final x just as a placeholder for a nondescript x. I'm sorry if that's confusing you some, but I can't get past the desire to follow the proper rules of calculus. And so for a nondescript function of x, this is what we would end up with, where I just remove the x final because it was a placeholder for my x variable. And this is the work done by a non-constant force.